All right. Now, we will start from the current slide in a minute. Let's see, is there any reason not to now? No, I guess it's okay. So let's go on and start from the current slide. But we're not going to start there yet because let me explain to those who were not here before. Last class, that was last Thursday's class, is out there. Where it goes ultimately is to YouTube. And how you access that is through Blackboard. Are all of you familiar with Blackboard? Anyone who is not? Okay. You go to Blackboard, the home page for this course, and they go to a new Blackboard, which has a lot of really dinky sounding tabs on it. Before, it was content. Everything you needed was in content. Okay? Here's another. And can I get your name, please? Cece, got it. Okay. There you are. Good deal. So let me explain. When you go to this class in Blackboard, there'll be a series of blue tabs on the side here. The first of the, well, not the first, but one of the early ones says, My Syllabus. Now, at best, last time it would just say syllabus. This is all fancy, My Syllabus. So if you click on that, you'll see the syllabus. Now, the syllabus you see there will not look like the one we did in class Thursday because, well, actually it will look sort of like that, but it'll be corrected. I've made all the corrections to it. I just realized since I did it that I do have one other correction to make, and this really affects this class. When I gave my office hours, I said on Tuesday and Thursday I have the 15 minutes before classes start, 7:45 to 8, and then I'm in class from 8 to 9:50. I have 10 minutes between 9:50 and 10. Then I have a 10 o'clock till 11:50. I have 10 minutes until 12, and then 12 to 1:50, followed by a lab from 2 to 3:30. And then I have the 30-minute drive over here, which I can never leave right at 3:30, or maybe I can next time because they're going to have a test, and hopefully they'll finish early. So I'm always pushed to get over here on time. But then I'm here from, this class supposed to start at 4 and go to 5:50, which I'm using the time now and I need to get on. But last time I told you I would be on campus, on the Bessemer campus, until 9 o'clock on Mondays and Wednesdays. So I'd be leaving here right after 5:30. Well, those two classes, the last two classes I had on Monday, Wednesday, I thought I might lose the early one because I didn't have enough students in it and it was going to stack with another class that another guy was teaching. But then I found out that he had a low class, the other one, that he needed to stack with my class, and I let him take that one too. So basically, now I get off at 6 o'clock on Mondays and Wednesdays. So what I'll do now is stay here after class until 6. Okay? So I'll have office hours. I'll just have them right here in this room from 5:30 till 6. And I'll stay later if anyone needs me to. Because there's nothing really pressing most days. So that's one change. Okay? And I didn't make that change. I didn't realize I'd have that time until after I'd already put it out there. I did say on the locator card, but I forgot to change it in the syllabus. So you can see the syllabus under my syllabus. Now that's in static form. Then you go on down near, on my computer, it's near the bottom of that page. It goes on to the next page. But there'll be a tab there that says Course Handouts and More. Really, again, a strange title. Okay? Now, I don't do course handouts there, but here's what I put in there. I put in there the other stuff I put in content earlier. And here's what's there. My locator card is there. That shows when I'm on campus, when I'm off campus, when I'm in class, when I'm out of class, when I'm on which campus or whatever. Okay, so that's there. Then I put all the PowerPoints. Okay, chapter 5, chapter 8, chapter 12, whatever the chapters are that we'll be doing, I put those PowerPoints there. Time out here. This book has terrible PowerPoint. I apologize for this. I did not choose this book. It was one that another school who was teaching this for stenography students said, yeah, this is a good book. And I didn't have a chance to review it. In fact, I didn't get to see it until after we had ordered them. The PowerPoint stinks. The book's not bad, but the PowerPoint is really terrible. So I'm going to check around and see if I can find something better. And then the test bank turned out to be even worse, but I can fix that. Okay. So the PowerPoints are there. I think that's about all that I put under that. Okay. Oh, one more thing. That's what I was getting at. The YouTube video link. Okay. And it just says Physics 112 YouTube videos. It's the last thing on that, under that. What did I say it was? Class handouts and more. The last thing on there is YouTube video. You click on that, and right now you'll see last Thursday's class. You click on that, and everything I say, everything is projected on the board. Now, we barely had time because last time on the other campus, Bessemer campus, there were people asking me questions, there were people that couldn't find classrooms, there were just everyone was coming by, stopping me, interrupting me, so I was here a half hour late at least. So we didn't have time to do much more than the syllabus, but we did finish the syllabus, right? Did we do the locator card? It shows when I'm in class, out of class, that kind of stuff. We did not. Okay. I basically just described it to you, but it's on a different flash drive. I'd have to take this one down and put it. So let's just, I'm here till, okay. Basically, on campus, 7:45 every morning. I've got 8 o'clock classes across the board. Basically, I'm in class until 1:45 on Mondays and Wednesdays, and I've got 1:45, and this was different because I lost the 2 physics classes, 1:45 till 6 office hours on the Bessemer campus, Mondays and Wednesdays. On this campus, on Tuesdays and Thursdays, I'm stacked. 4 classes in a row, 1 with lab. This is the last one, so at the end of this class, 5:30 until 6, I have office hours here. Okay. Fridays, and the only 2 Fridays we're going to have left, I was on campus last Friday, and I'll be on campus this Friday, and the only Friday that ends the term in August. During the rest of June and all of July, the campus is closed on Fridays. These are old buildings. They take a lot of energy to air condition, and, you know, population is down, so we did away with Friday and Saturday classes, okay, in the summer only. So tomorrow and the only Saturday in August, I'm on the Birmingham West campus, Dr. Pruitt's office. That's B122. That's in the academic building on that end of the building. B122 from 7:45 to 11:45. Usually I'm there later, but that's what I have to put down. All right, so any that weren't here before, you can see what happened last time on that. But that's basically all we went over. Okay, now, the one other thing I always like to do at the beginning of a class, and I didn't have time last time, is go over safety issues. Okay? 3 forms of safety we have to keep in mind. Nothing we're going to be doing requires any special safety. But what if there was a fire? Okay? Hopefully not. Fire or a chemical spill, something happens in the building, we need to evacuate. Where do we do? How do we go do that? Well, let's say first that what if the fire started in here? My computer blows up and catches pieces of paper and things like this on fire. What do we do? What would be our procedure? Yeah. Several things we really should do. What would be some of them? Find the fire extinguisher. Does anyone know where the closest fire extinguisher is? Yes, in the hallway, very, very close to this classroom. I'm touching the bottom right here. You can't get much closer to that. Okay? So somebody get a fire extinguisher. How about what else? If it started in this room. Pull off our alarm. Where's the closest fire alarm? Okay. Right across the hall, right next to that. Within sight of the door. Red box with the key. There's the fire alarm. get out of Dodge, okay, right? We don't want to be in here with a fire. We pulled the fire alarm to warn everybody else. Oh, one other thing we should do. Now, if you have the campus police on speed dial on your phone, that's a very good thing. Very safe thing to happen in case any kind of thing happens. If you have campus police on your speed dial, you can dial it. If you have that, you do that as well. If it started in here, they need to know about it first. If you don't have their number, you don't have it speed dial, then dial 911. Okay? They won't be happy because they like to know first, but we don't care about happiness. We just need it. So someone's dialing 911, someone's pulling the fire alarm, someone's getting the fire extinguisher. I'll stay in here and fight the fire. Now, all of you look pretty able-bodied now, but what if somebody twists an ankle or messes up the knee or something, and you need some help getting out? I will be the last one out. We evacuate the building. The best way out is probably just how you came in. Go out here, hang a right, and go out the main entrance. However, there's another exit right there and another exit down there. So we're right in the middle of three very close exits. The best one to take would be the main one. Biggest doors and that kind of stuff. If you go out this one, you're caught in the L of the building, and if there was a major fire, you could get explosions from either side. So it's best to go that way. And where they want you to go is across into the parking lot that's just across the road. You'll see the parking lot right over there. You all go together, stay together. Don't trample one another, that kind of stuff. I'm the last one out. I'm bringing my roll book with me because when we get out there, I have to call roll. And if somebody said, hey, fire, no more class today, I'm out of here, and we don't know where you are, so we have to assume you're still in the building, and therefore someone, fire professional or me or somebody else, has to come into a burning building to try to find you. Okay, so don't leave. Stay together until we call roll and get word what's going to happen next. Okay. So there's fire or chemical spill, anything that we would hear the alarm here in the building. What's another potential safety issue? Weather, okay? And this is the season. We've just had a tropical system come through. If it was a hurricane, that could have produced tornadoes, okay? If that would take flash floods or severe thunderstorms, that kind of thing, if that would happen, what do we do? Think always low and interior. Okay, guess what? We're on the bottom floor. You can't get any lower than this, but we're on the exterior. There are plenty of tree limbs that can be broken off and sit through these windows. We don't want to be here then. So about the safest place for it to be would be the hallway right out here. Okay? It's interior. The walls are relatively close together. Don't go to the lobby or any other place that has windows. Okay, so stay in the hallway. So we just go into the hallway, pretty safe, and park yourself along the wall. The walls are the greatest strength. Okay, so that's where we park. And again, you stay together. You don't say, oh no, my dog's outside, I got to run home and get no. Save yourself, save your dog, don't get in the car. Okay, the dog will take care of itself. The animals have plenty of sense. So, stay there, and again, I'll be the last one out, helping whoever the last person is the slowest person to leave. I'll carry my roll book, and I'll call roll again if we can't find you. Someone has to come back, start searching the building to see what happened. So, just outside the door, I can leave. Okay, that's the second. Third, the second. What's the third safety issue that I never, ever crossed my mind until recently? Active shooter. There, folks, we've got some problems. What is typically the thing you do if there's an active shooter? Lock the door and get out of sight and get very quiet. We can get out of sight and get very quiet. I would say this corner right back there would be best. The trouble is, I have no way of locking that door. They don't give us keys. In fact, there's a thing on the outside of the door that says, do not lock the classroom doors. So I don't know even if they can be locked. So I have no way to lock them. Okay? I asked the department chair here in charge of the building, what do we do in case of active shooters? You say, yeah, you can't lock the doors. Put things against the door to keep them from getting in. I said, but this door opens out. You can't put anything against it to keep them from going out. So, if we hear shooting that way, I'm trying to help y'all get out this way. Okay? And if it's coming from that direction, I would say, run over to that building and find a safe place there. If it's coming from this direction, run that way and find a safe place. Because we have no defense in here. But we're on the first floor, so at least we're not on the second or third floor. There's nothing to do. So that's what I would try next. I think there's a way pretty easily to get out these windows. Because they're pretty big windows, and it's not a bad drop there. Okay? So hopefully we won't have to go there. But there's nothing we can do here. We can't lock. We can turn off lights. We can turn off cell phones. And we can get very quiet. Hide back here or get out of town. Okay? That's the way possible. And run folks. And if it is, again, I'll be the last one out. So if he comes in, I'll do everything I can to stop him. Y'all get out of here. You're the future, I'm the past. You get out of here. Okay. So there's the safety issue. Sorry that did sort of a fast job on it. Okay. Any questions? Okay. We did go over last time what the syllabus says, the course description, and the first thing it mentions that comes out, it talks about electricity and magnetism, but says you need to understand the basic principles of forces. So we're starting in chapter 5 with a force. Okay? And again, these are miserable, miserable PowerPoints. Okay. I'm going to hit some highlights that are not done here. What is a force? Can anyone give me a simple, straightforward, easy to remember, or any kind of definition of a force? This picture almost illustrates one type. Okay, it usually involves movement, but not always, but usually does. A force is a push or a pull. This guy is pushing on there, therefore he's exerting a force on whatever that is, okay? I can't tell what it is, okay? There's several forces involved here. If he's really pushing, he's pushing against the road here with his foot, okay? That's where he gets it from. He's pushing with his elbows, he's pushing, or his arms, he's pushing. So a force is a push or a pull. He could be pulling on it. That would also be a force. Whether he's moving it or not, he's still exerting a force on it, okay? So a force, simply put, is a push or a pull. Now, a little bit more detailed on what a force is. It's a mass times an acceleration. Okay, that's the definition of a force. Okay, now what do we mean by mass? Any ideas? What's a mass? Is it really hot in here to y'all? I swear. Do they have air conditioning here? I see no thermostat or anything here. Whoa. Sorry. Okay, what is a mass? Second? I'm hard to hear.
Density of an object.
Density, is that what you said? Okay, it has to do with that. That's a pretty good term there. But density is a little more specific. Mass is just how much of a substance you have. Really simple. How much of a substance you have. Now, that's different from weight. Weight is a force. Mass is just how much of a substance you have. Okay? Now, we have two major measurement systems. What are they? Different ways we measure things. Metric system? And what? SI is metric. Okay, that's SI. And then the one we're used to, the good old U.S. customary, used to be called the British system. Maybe still be called the British system. Okay? Now, in the SI system, mass is very well defined by the unit gram, but the basic unit is actually kilogram. A gram is a tiny amount of mass. A kilogram is 1,000 times that, so kilo means 1,000. So a kilogram is the basic unit in the SI system. The metric system would probably be the gram, but in the SI system, which is based on that, is the kilogram. It's the only one of your basic units that has a prefix, kilo, okay? In the U.S. customary system, there is a unit for mass, but I bet you've never used it. What would you say it was? So what do you measure mass with in the U.S. system? Did anyone guess pounds? That's a weight. That's not a mass. It's equivalent, but it's not the same. So the unit for mass in the U.S. customary system is a slug. S-L-U-G. Have you ever gone into the grocery store and said, I'd like a slug of ground beef, please? No. They would think, why do you want a ground up slug? No, that's not what they would think. But we don't use it in the U.S. customary system. It's just not a term. There's not even an abbreviation for slug. If you ever use slug, you have to write out the whole term slug. Pounds is LB, feet is FT, inches is IN, meters is M, grams is G, kilograms is kg. Everything has units but slug. It's not used, nobody uses it, so they don't even have a unit for it. But that's mass, okay? Mass times acceleration. What in the world is acceleration? Any ideas? Say again? Okay, it has to do with speed, but it's different from speed. Good guess. Okay? Let's start something simple. Let's say I went from here to there. How would you describe that? Going from here to there. A distance. Very good. That's a distance. Now, another way you could describe it is a displacement. I was here, I would displace myself till I was here. Now, those sound like the same things, right? Distance is just a number, how far you went. Displacement is how far you went in what direction. So we have some things that sound almost the same, but some are just quantities, like distance. Others are quantities with direction. Those are called vectors. Now, we're not going to get into vectors much in this course, but realize they're there. Displacement is a vector quantity. Distance is just a scalar quantity. A vector quantity has a scalar amount with a direction. Okay? For instance, I drove from home to Bessemer this morning. Let's just say 20 miles. That's the distance. 20 miles to the southwest, that's the displacement. Distance with direction. Okay? So, I'm not going to get into this too much, but I just want to let you know that. Okay, so I could measure the distance it took me to get from there to there. What else might I choose to measure? The time it took me to get from here to there. Okay? And then if I took the distance and divided by the time, what would I have? Someone said it earlier. Distance divided by time. Okay? Say again? Speed, exactly! Okay? And speed, again, is a scalar quantity. It's just a number. Like I said, if I drove from home to Bessemer, and it was 20 miles, and it took me, let's just say, something easy, 40 minutes, okay? Then that would be 50 miles an hour. Okay, well, is that right? Yeah, I think so. Okay, that would be my speed. But if I wanted to talk about velocity, sounds like speed, doesn't it? But velocity is a vector quantity, 50 miles per hour to the southwest. Okay, so it's just they're the same kind of concept. One's a scalar, magnitude only, and one's a vector with direction. Okay. Again, we're not going to get into that too much here, but just to throw it out so you get the concept. So, what we call that is a time rate of change of displacement. That's velocity. Time rate of change of distance, that's speed. Time rate of change. You divide the distance by the time and you get speed. Divide the displacement by the time, you get velocity. Okay, we're close now. Acceleration is the time rate of change of velocity. Because when you accelerate, you're changing your velocity, right? It's not just changing, it's not just your speed, it's how much you're changing your speed. Because when you accelerate, that's when you're at a stop sign or a stop light and it goes green, you accelerate, right? You push down on the accelerator, right? That's the way you move, okay? If you're passing a car, you accelerate. You change your velocity in order to get around the car. That's an acceleration, the time rate of change of velocity, okay? So, let's get some... Goodness, it's hot in here. Maybe that would help. I have a feeling it's warmer outside than in, or is it? If it's cooler outside, let's open the window too. Yeah, it's cooler out here. I usually close doors because I talk so loud that because I'm hard of hearing, probably. And so I try not to disturb people, but I don't see many other classes going on. Let's just see how the temperature feels outside. With the sun coming in like this, I have a feeling it's warm, not warm. Yeah, that's pretty hot. Okay, so here's what we have. Let me write on his thing he's pushing here. Okay, we have first mass, and the symbol for mass is usually M, okay, and the unit for mass in the SI unit is kilogram. That's how much of an object is. What's the mass of that thing? Is that a cardboard box? Maybe so. That's its mass, how much of it there is. And by the way, mass is a scalar quantity. It's just a number. Okay, there's no direction associated with mass. Okay, then we have acceleration. But acceleration comes from distance, which is a scalar quantity, or displacement, and that's the vector quantity, and that's usually measured, and it depends on what direction. That could be measured, the symbol could be X, Y if it's falling downward, or Z could be falling downward. S, there's all sorts of units you could use, not units, symbols you could use for displacement, but the unit is in meters in the SI units. Okay, these are the symbols, let me see, and these are the units. Okay, this is the quantity. Okay, so kilogram is the unit, meter in the SI units, okay, or usually feet in the U.S. customary, but it could be yards or miles or something else, okay? But the most common is that. Okay, and then we have time. Okay, that's what we're measuring. The symbol for time is little t. Don't put capital T. Capital T will be temperature, though we probably won't do too much with that, but little t is time, and that's usually measured in seconds, in both the SI units and in the U.S. customary units. Time is universal. Seconds is the units. Okay? Now, that doesn't get us acceleration, but first, if you do the time rate of change of distance over time, this is speed. Okay? I'm going to put SPD so you don't think it's the same as displacement down there. But displacement over time is velocity. Little v for velocity. Capital V stands for volume, okay? Little v for velocity. The units for this, for both of those, would be meters per second, or you could have feet per second. Or you could have miles per hour, kilometers per hour, furlongs per fortnight, whatever, okay? Distance divided by time. That's a speed or a velocity, okay? Velocity being a vector quantity. And then finally we get to acceleration. And acceleration is velocity divided by time. The time rate of change of of changing your speed. Okay, so this will be in meters per second, which sometimes we call meters per second squared, or feet per second squared. Or you have others. I'm guessing that probably no more than one of you really are into hot rods, or fancy cars, are you? Okay, if someone's really bragging on their car, have you ever heard, it'll do 0 to 60 in 4.3 seconds? Have you ever heard anyone make some sort of comment like that? What are they describing there? What's 0 to 60? Say again? Well, actually, when they say 0 to 60, that's 0 miles per hour to 60 miles per hour. From a stop to 60 miles an hour in 4.3 seconds. Number one, they're probably lying. No, I'm sorry, I wouldn't say that. But if it's a really souped-up car, you could do that. Well, what do you got? 0 to 60, that's a change of speed in a certain time. And that would be in miles per hour per second. So that would be miles per hour per second. That's also an acceleration. That's how you measure things like that, acceleration. So that is then your acceleration is acceleration. That would be, I'll just put the symbol A, and that'll be meters per second squared, or feet per second squared. Those are the most common, but SI is meters per second squared. Say again? I can't hear you. For acceleration, yeah, that's usually the symbol. So when we're talking about a force is a mass times an acceleration. Mass up here times acceleration down there. Which the basic units for a force would then be meters. I'm sorry. I get talking faster than I'm writing. Well, or thinking or something. Okay. Mass is kilograms, meters per second squared. Okay? Now, that has its own special name. That unit has its own name. And that is a Newton. Now, why did I capitalize the N for Newton and none of the other units I've capitalized? Any ideas? Where do you reckon they got the say again? Newton's law? And who was Newton? A person! Sir Isaac Newton. So units that are named after people are usually capitalized. So a Newton is capitalized, capital N. And even though he really didn't talk about forces that much, I don't think, I didn't read his work because he wrote in Latin. I don't read Latin. But they named the unit for force after him, Newton. So you don't have to do kilogram meter per second squared all the time. You could just do that. Now, in the U.S. customary system, the unit for force is the pound. Okay? And that's LB. Don't ask me where LB comes from. I don't know, but that's what pound. You know that. You see it all the time. But where did that come from? I have no clue. It's probably Latin or somewhere. But a pound, I think, is technically a slug foot per second squared. I can't swear to you because I never deal with slugs, but that's where it is, a mass times the acceleration. But we never use that. We usually just use pound when we're talking about how much something is. It's not really a mass unit, it's a weight unit, as is Newton, a weight or a force unit. Okay? Now, okay. That's the first word is force, okay? That's how long it took me to get through that. Okay. Now, and if you got your book, I don't really see too many. Now here's, oh, I do see a few. Okay. And do you have an e-book? Oh, okay. I saw your computer open. I thought you might. I got another phone call today, and it was in the 10 minutes in between two classes. I thought, how can people catch me in the office like this? But that was the secretary here in this building saying, I think she got a call from the bookstore manager saying, your physics students are not buying very many books. Do they need the book for the course? I said, well, it's up to them. They could use an e-book. They could rent a book. They could do any way they want to do it. They don't have to buy it from the bookstore. But I said the first day of class, hardly anyone had a book. I don't know if y'all had yours, but that's been in all my classes. In fact, my afternoon class before this one, out of a class of probably 15, only 2 people had books, you know. So early in the term, I realized not everybody has the money to pay for them. But she was complaining, or I guess he was complaining to her that not that many students had bought books, and that she said, and they need them to pass the course, don't they? I said, well, that's up to them, you know. So I don't know if you hear anyone say that. I just thought I'd bring that up. Okay. But Isaac Newton is mentioned here at the top, and you can read a little bit about him. If you want to dig in further, of course, you can find other sources to do that. Okay, now we mentioned 2 units here, newtons and pounds. Now, we usually give equivalences here, and I'll give them to you now. 4.45 newtons is 1 pound. Okay, so in other words, a pound is a bigger unit than a newton is. Okay, and why would that be the case? A meter is a bigger measure than a foot is, so a slug must be quite a bit more than a kilogram. But we don't deal with those, so don't worry about it. But just for your cultural thing, you have a pretty good idea about what a pound is. I would say this book is probably a little bit more than a pound. It's probably a little bit less than a newton. I'm sorry. More than a pound, so it's a little bit, you know, maybe 5 newtons or something like that, just to get an idea. Okay. Now, who answered the question about who Newton was and said Newton's laws? Is that you? Okay. Glad you brought that up. Does anyone know what Newton came up with a paper? It was more like a book, okay, that was absolutely groundbreaking. It took physics off some nebulous, uncertain, mushy kind of science into a really well-defined, unified science. Now, he did a lot in this paper. It was called Principia, which means principles of natural philosophy. Principia, and somehow is in Latin. And basically, he defined the 3 laws of motion. Before this, way before this, there was a guy named Aristotle. And whatever Aristotle said, everybody believed. He was probably a couple hundred years BC. Newton came along maybe 1400 AD. But in between that, everybody just, if Aristotle said it, everybody believed it, swallowed it hook, line, and sinker. That was before science was really a science, okay? Science means you test things. People didn't test. If Aristotle said it, they believed it. Well, Aristotle had just observed nature, but never experimented with nature. That's the big difference. And in his observation, he noticed that a cannonball and a feather, or a piece of paper, fell at different rates. So therefore, it said heavier objects fall faster than lighter objects. And everybody believed that for years. Well, the generation before Isaac Newton, there was a guy, an Italian guy, named Galileo. You probably have heard of him. Galileo didn't like to take anyone's word for anything, okay? He tested everything. He was literally, probably in many senses, the first real scientist, because he wanted to test everything. And what he did, he tested and had someone take a cannonball and probably something more like a baseball and dropped it off the, supposedly, the Leaning Tower of Pisa in Italy, because that's where he was from, and sure enough, they fell at the same rate. And the baseball, it wasn't really a baseball, it was some small ball that was supposed to cannonball. said, look, they fall at the same rate. Where was Aristotle wrong? Well, he was using something very light that had a large surface area, and there was a lot of resistive force behind it, air resistance. Okay? That's what was making it fall more slowly, not the fact that things fall at different rates. So he came up with this idea, Galileo did, and it was actually Newton's first law of motion. But Galileo actually came out with it first, but he didn't expand on it as much as Newton did later, and then Newton added two more laws to it, and they were attributed to Newton. But this law is called the law of inertia. What in the world is inertia? Can I erase this stuff for now, because I need something to write on? All right, to erase? Okay, the term inertia. Okay, what in the world does that mean? Ever hear it before? Oh my goodness, here we have a good answer, okay? What did you say? A property of a body that causes it to remain at rest if it is at rest, or to continue moving when with a constant velocity unless an unbalanced force acts on it. Whew, pretty long definition. Now, I would almost hazard a guess of where somebody may have heard the term inertia is, what's the first 5 letters in inertia? Inert. In other words, that body at rest is staying at rest. Why are you so inert today? Maybe no one said that to you, but I bet you they thought it, okay, on a Saturday morning or something like that. You just can't get moving. Oh, I have too much inertia, okay? That's how we usually think of it, okay? And that is a proper way to think of it. It's the property of an object to remain at rest if it is at rest, or to keep moving at a constant velocity if it's already moving. Think of, I'm rolling a bowling ball to you. If you don't move, you get hit, because nothing's going to change that bowling ball coming to you. It's got that much inertia coming at you, okay? So, inertia is that property. And that basically is Newton's first law. An object at rest tends to remain at rest unless it's acted on by an unbalanced force. Hey, this stool is at rest, isn't it? Now it isn't. Why? I did an unbalanced force kicking the stool. A push or a pull. That pushes it. Now I'm pulling it back. So that's what's changing its inertia. The inertia is the tendency to remain where it is. Or if I rolled the bowling ball down the floor here, unless it's met by some unbalanced force, your toe, a chair, something else, it's going to continue rolling in a straight line until it is acted on by an unbalanced force. That's the property of inertia. That's Newton's first law, actually originally stated by Galileo. Okay. Now, this is figure 5.1 here. I can tell that guy is pushing. He looks like he's straining it, doesn't it? Okay? Or else he's faking it pretty good for the picture. Okay? They have 2 arrows there. Okay? Now, I'm going to push on this table. Okay? I am pushing. Believe me, I'm pushing on the table. But it's not accelerating. I'm exerting a force on it, but it's not moving. Okay? Why? Because there's an unbalanced force, that wall, okay, that's pushing back. And guess what? The wall wins. Okay? I'm not going to push it through the wall. I'm not going to try. I'm not going to push hard enough to break the table either. Okay? So, here, if these arrows are correct, he's pushing on the box, but he's meeting, you can see this is pretty rough looking pavement here, and that has friction. And if he's pushing there, just like me pushing on the wall but not getting anything, there's an equal and opposite force pushing against them. So this does have an unbalanced force because he's exerting a force on it, but it's not moving. And a force is a mass times acceleration. It should be accelerating, except there's an unbalanced force keeping it from accelerating. Now that's my best guess of what that is done, the pushing force and the frictional force cancel each other out, making a zero acceleration. Okay. Now that leads to another example. Okay. Let's say, I guess most of you drove here today, right? Okay. Now, I did too. And when I was traveling along, let's say the interstate this morning, because there I was going at near a constant speed, let's just say 70 miles per hour, and hope I was within that, okay? And I was going along, and I was at constant speed, so I wasn't accelerating. Does that mean there was no force on the car? Yeah, there was a force. If I lifted my foot off that accelerator, it was going to slow down. Wait a minute. I thought Newton's first law says an object goes at a constant velocity unless it's opposed by an unbalanced force. Well, the deal is there were unbalanced forces. There's wind resistance and there's the road resistance. If you can hear the tires going on the road, there's road resistance. Anything that has resistance. So there were two forms of resistance. Resistance of the road and resistance of the air. And if I didn't keep accelerating, now my net force was zero. I know that's true because I was at a constant speed. If you're at a constant speed, there is no acceleration because acceleration is change of speed per change of time. And if I'm not changing speed, I'm not accelerating. I was exerting a force, but it was balanced by equal and opposite force. So that's what we mean by unbalanced forces. If there was an unbalanced force acting against it, like the wall or something like that, then I'm not creating an acceleration. Now, they have a couple of pretty nice activity here, and this is not a bad one. Take a postcard and put it over a glass, okay? And then put a coin on top of the postcard, okay? I don't have anything as stiff as a postcard. Let's see. Can I try it on your glass? What, this? Huh? This? Okay, let's try it. Okay? All right. Now use your glass. Now do you mind if I goes in it? Your finger. Okay? Here's a finger. Okay? Never done this, so I don't know if it will work. But if I take this and pull very rapidly, what does the thing do? It went into the glass. It didn't stay on top of here. The reason is because, oh, and now I've got to stick that back on the board. Why didn't you tell me that? Okay? You just wanted me to get my hands messed up. Okay, you sure don't want to drink this now, do you? Okay. So, the inertia of the pen kept it in place. Even though the paper moved, it didn't, and it fell into the glass. That was an example of inertia at work. The tendency of an object to remain in place, zero motion, unless acted on by unbalanced force. Now, it may have moved a little because there was a little bit of friction between the pen head and the paper, but not that much. Okay? You missed our great demonstration. Okay. All right. So mass is a measure of the inertia of a body. We said how much of the object that was there. It's also a measure of inertia. Okay? Because think of this. You ready, Sydney? I'm going to throw a ping pong ball at you. You ready to duck? Yeah, right. You aren't going to duck. But if I was going to throw a bowling ball at you, well, I wouldn't get it that far anyway. But, okay, if she was close enough, okay, she would duck or move. Because the bowling ball has a lot more mass, its inertia would be a lot more to stop. And she didn't want to stop it with any catching it or anything. Okay, so ping pong ball wouldn't even make it there either, would it? The mass is, another way to mention mass is the measure of the inertia of the body. Okay, and they have a picture of a transfer truck, big 18-wheeler, and a little sports car. Which has more inertia? The 18-wheeler has a lot more mass. You're absolutely right. Okay. Now, okay, it jumps to figure 5.6, and the last one we had was 5.1. Okay, you see how good these are? And almost nothing of the important stuff. So the law of acceleration, and by the way, this is Newton's second law. That was his first law, law of inertia. Second law, if there is an unbalanced force acting on an object, we'll call that F sub n for net force, then that is equal to the body's mass times the body's acceleration. Okay? That's what I told you before. A force can be described as a mass times acceleration. Okay? But you can have a force even if you have no acceleration. A force is technically a push or a pull. Okay? But if there is an unbalanced force, a net force acting on an object, then that's equal to the mass times the acceleration of the object. Let's just say that suddenly someone put down some ice underneath there and he's pushing like that. It's going to take off because now there is hardly any frictional resistance and he's exerting a force, so now it's going to accelerate like crazy. He'll probably fall flat on his face too. Wouldn't you like? No, you wouldn't like to see that. Okay, so there's Newton's second law. If there is an unbalanced force, net force, then the body is going to, what did we say before? An object at rest will stay at rest, or an object in motion will stay at constant velocity. That's the first law, unless there's an unbalanced force. If there is an unbalanced force, then it's not going to stay at a constant velocity. And if it's not at a constant velocity, what does it have? Time rate of change of velocity? Acceleration, exactly. So that's where this comes from. And again, I don't think Newton himself used these terms because of something I know about him, but we'll not get into that. So let's talk about, and I think we've already did this, that this would be a mass times acceleration, SI, this would be kilograms meter per second squared. There's the mass, there's the acceleration, and this is a Newton. The unit is a Newton. The symbols are MA. The unit is kilogram meter per second squared. Okay? So 1 Newton is 1 kilogram meter per second squared. Okay. And in the U.S. customary, it's what I said before, 1 pound is 1 slug. I can't even write it. Slug feet per second squared. Yeah, what are you doing here? Slug foot per second squared. Okay. Just like I said before. We never use slugs. Ever. Now, they mention another couple of units here. I don't think you really know this, need to know it, but if you ever did, if you use smaller units, see, a kilogram is a pretty large amount of mass. That's about like this book, okay? A meter is a pretty long distance. That would be basically from my ear to my fingertip here. That's about a meter, okay, approximately. And second, is a pretty small amount, so it's a pretty good sized thing. So that's a fairly large amount of force. If you're measuring really small things, you sometimes will use a dyne, D-Y-N-E. I don't know if that even has an abbreviation either. And that is 1 gram times a centimeter per second squared. Okay? Again, a mass in grams, a very small amount of mass, very small distance. A centimeter is about the distance across your little fingernail, and per second squared. That's moving really slowly. So that would be a dyne. I don't think it's necessary. I just said it because it's in the book here. Okay? Not an SI unit. Its use is less common. So, what I want to do now is do example 1. What force is necessary, so we're looking for force, that's the unknown here, is necessary to produce an acceleration of 6.0 meters per second squared. Now, how do you know that's an acceleration? Well, they told you is one thing. What the other? The units give it away. Distance per time is always acceleration. Meters per second squared. Okay? On a mass of 5 kilograms. Okay. Time out a moment here. Why in the world do they have all these zeros in there? Isn't 6.00 meters per second squared 6? And isn't 5.00 kilograms 5 kilograms? Yeah. Why do they have those extra zeros there? They're put there indicating significance. When you put this on the scale, it didn't just read close to 5, it read 5 to the nearest 100th of a kilogram. In other words, to the nearest 10 grams. It was 5.00 kilograms. Same thing there. That's significant. And we call that significant digits. That's a measure of precision. So if you have 3 significant digits here, 3 significant digits there. And what is force, by the way? Do you remember the formula? Look right up here. It's mass times acceleration. So you just plug in 5.00 kilograms times 6.00 meters per second squared. I don't have enough room here. What does that give you? 30.0, what unit? Kilogram meter per second squared. But what is a kilogram meter per second squared? Newton. 30.0 newtons. Now, why do you only have 1 0 there? You had 2 in the others. You count the number of significant digits. You had 3, that's 3. If you put another 0 there, that gives you 4. You can't get more significance out of a problem than you put into the problem. So that's 30.0 newtons. That's how much force you would need to give 5 kilograms an acceleration of 6 meters per second squared. Okay? Make sense? All right. Let's clear that screen. Do you have it? Anyone need it a little longer? Okay. Okay. So, example 2, I'm going to clear this. Hot. What force, again, we're looking for force. What force is necessary to produce an acceleration of 2 feet per second squared? By the way, that's a much smaller acceleration because a foot is about a third of what a meter is. And we had 5 or 6 before, and this is only 2 feet. This, okay. Of a mass of 3.00 slugs. I have no idea how much mass that is because I never use slugs. But we're just doing problems. So what would be your formula? Mass times acceleration. And what would that be here? 3.00 slugs times 2.00 feet per second squared. Okay, and that would be what? 6.00 what? You could write slug feet per second squared, but what is a slug foot per second squared? Pounds, exactly. 6 pounds of force. Okay? 6 pounds of force. All right? Everybody got it? Any questions? Okay. All right, to erase. Example 3. Oops. Example 3 says, this time find the acceleration. This is your unknown this time. Produced by a force of 500 newtons. So now we know the force is 500 newtons. Now if they just wrote that down, this is ambiguous. That could have only one significant digit. It could have 2 or it could have 3. We don't know. Anything following a decimal point, you know it's got to be significant. In front of a decimal point, you don't know if there's zeros. Now, if they were numbers, you know. But if there's zeros, you don't. So in the book, they put a bar over it. What does that bar mean? The second zero is significant, so everything in between the non-zero number 5 and the significant 0, they're all significant. So 3 significant digits. Okay? Find the acceleration produced by a force of 500 newtons applied to a mass of, so the mass is 20.0 kilograms. Okay? Now, what do we do with that? Well, let's go back to the formula we had, which was force equal mass times acceleration, right? We know that. This time we're trying to solve for acceleration, so it might be a good idea to first solve for acceleration here. So how would you solve for acceleration? Divide both sides by the mass. Okay? The masses cancel out here, and you have acceleration is equal to force divided by mass. That's what we'll use down below. Now, anytime you have a relationship like this, and there's tons of them in physics, where you have one value is equal to the product of another two value, you can use this little trick. Okay? And here's what the trick is. Either draw a triangle or a circle. I don't care which, or whichever you prefer. Draw a dividing line that splits it in two, and then draw a vertical line here. The vertical line is going to be your multiplication. The dividing line is dividing, right? Something over something is divided by it. Put the thing that stands by itself here, force, or here, doesn't matter which, and then put the two things multiplied down here. Mass times acceleration. Mass times acceleration. And guess what? Now you know the relationship. If you're looking for force, cover the force. Force equal mass times acceleration. Yeah, there it is. If you're looking for mass, force divided by acceleration. If you're looking for acceleration, force divided by mass. That's exactly what we got. It's a nice little trick that works with lots of formulas. If it's one thing equals something multiplied by something else or divided by something else. If you start with either one of those, so one thing's equal to a product of two things, or one thing's equal to a quotient of two things, you can use these little either circle or triangle, whichever you prefer. So that's another way to get there without having to go back and divide each time. Okay? So now let's use this formula. Acceleration is equal to force divided by mass. And what's your force? 500. Now, I'm not going to write newtons down because newtons is a derived unit. I want to write down my fundamental units. And what were the fundamental units of the newton? Kilogram, meter per second squared. Perfect. That's what a newton is. That's the same thing. Divided by your mass, which was 20.0 kilograms. Okay? Units are your friends, folks. Be kind to them. Take care of them. And they'll take care of you. Okay? So 20 go into 500. Well, one thing I'm going to do to make my math a little easier, I'm going to move this decimal one place that way, move that decimal one place this way, and that's 2 into 50. That's easier. What's 2 into 50? Second? 25. So 25.0 because you need 3 digits there. You have 3 digits everywhere else. And notice your units. The kilograms cancel out, leaving you meters per second squared. And that's a great unit for an acceleration, isn't it? It's fun, isn't it? Okay? Make sense? All right, good deal. Let's see if they got, oh, look at that. They got it right in the book. Good for them. Okay? Now, they go off to the side and do a conversion thing. Seems like it's a little ridiculous, but this is how I do it. I just write down, rather than newtons, write down what a newton is. All right, now, there are homework exercises. Now, I have to always go back and check because different books use different things. This is 5.2. Let me just check and see. 5.2. Yeah, they do the odds. Here's some problems at the end of the chapter. If you got a book, it's on page 127. I would say try to do any of the odds 1 through 7. Okay? Try to do any of the odds 9 through 15. And then try to do any of the odds 17 through 33. There's a whole bunch of them there. You don't have to do them all, but try to do some of those. Okay? Okay? On page 127, any of the odds 1 through 7. Then on page 128, any of the odds 9 through 15. And then on 128 also, any of the odds 17 through 33. Okay. Now, let's look ahead. Now, for those who just came in today that weren't here last time, amazingly, this class said they preferred take-home tests to in-class tests. Wow, I was shocked. Okay, let me tell you a little bit about your test. Your test will be a lot more like these problems in the book than they will. I'm not going to give you fill in the blank or matching or multiple choice or things like that. It's going to be solving problems. But guess what? You have your book, you have it open, you have your notes, you have YouTube videos, you have all this stuff, so use them. Okay. Now, the next topic here is 5.3. I see people looking at the clock. We don't have a lot of time. Let's just take a look at a concept here. We probably won't get very far, but let's use all the time we got. I hate to cheat you out of 1 penny of your tuition dollar. I'd like to give you your full measure. Okay. The title of 5.3 is Gravity and Weight. Okay? Now, when we were talking about the formula we've been using, force equal mass times acceleration, that's the net force acting on a body, is the mass of the body times the acceleration of the body. If the body's not accelerating, the net force is 0. That doesn't mean the forces aren't 0. When I pushed on the table, but it didn't move, its acceleration was 0, that didn't mean I wasn't exerting a force. It means my force was equal to the force of the wall pushing back. So they cancel each other out. The net force was 0. When we're talking about gravity and weight, gravity is really the force due to gravity. And weight is a measure of that force. Now, that may be a net force or it may be just a component force. When I stood on the scales yesterday morning, I wasn't accelerating, was I? I was still. So does that mean my weight was 0? No, it didn't mean that. I wish, but it wasn't. It was way too much, okay? And what I was measuring was basically measuring how much force that poor little spring in there had to push against, and it moved up that far, because it was a spring scale, and that's what I was measuring, okay? No acceleration. The net force was 0, but my weight was how much gravity was pulling down on me. It was gravity's fault, not my fault. Not that I had too much mass, it was that. So that's what we're going to be talking about with gravity and weight. The weight of an object is the amount of a gravitational pull exerted on the object by the Earth. Okay? If that force is not balanced by other forces, the acceleration is produced. However, if it is balanced, like I'm standing on a scale or whatever, then you measure how much that force is. Okay? Now, they give an example here of you're holding a brick. Okay? Now, if you're holding a brick like this, I guarantee you got force between your fingers and the brick. Otherwise, it would fall, right? So you're exerting a force on the brick. How much force would that be? The weight of the brick. Okay? Because if you release it, it's going to start falling. It's going to accelerate, and the mass times acceleration will be the weight of the brick. Okay? So, when you're talking about weight, the book uses this symbol for it. F sub W. That's a little w, and that means weight. The force of this is the mass of the object times little g. Does anyone know what little g is? Second? Okay, no, okay, this isn't a unit. This is a symbol. The unit for like 7 grams, that would be little g. That's a unit. This is a quantity. And this is acceleration due to gravity. Because guess what? A force is a mass times an acceleration. So g is the acceleration due to gravity. That produces the weight. And let me give you what the acceleration due to gravity is. In the SI units, g is equal to, let me give it the same way they do in the book, 9.80 meters per second squared. Those are the SI units. Okay? If you're in the U.S. customary units, g is equal to 32.2 feet per second squared. You know those are accelerations because of those units. Distance per time per time. Those are accelerations. 9.80 meters per second squared, 32.2 feet per second squared. Now they also do something else here. They put in parentheses here, if you've got book, they put Earth. Wait a minute. Where else are you going to be? Well, one of you might one day be an astronaut or something. So you might be on the moon. This isn't the acceleration due to gravity on the moon, only on the Earth. Okay? That means anywhere on the Earth. Bottom of the Dead Sea Valley or top of Mount Everest, it's going to be really close to that same unit. Okay? But if you're on the moon, if you were on Mars, you're dead. But no, I mean, if you had, right, yeah, you could do that. Venus, you'd really be dead, or you'd be fried if you were, if you're any other body, you're going to have a different acceleration due to gravity. And that's a difference between mass and weight. Your mass is your mass is your mass. That's how much of you there is. That's your inertia, measure of your inertia. Weight is depending on what gravitational field you're in. Most of us, all our lives, are going to be in the gravitational field of the Earth. So that's why on the scales in the grocery store, it'll say pounds across here and kilograms down there, different numbers. This is mass, this is weight. The reason is, in the grocery store as anywhere, this is a constant. So they're equivalent to each other, but this is a force quantity, this is a mass quantity. Okay. I squeezed in a couple of extra things, didn't I? Okay. All right, we'll begin next time with example 1 on page 129. Okay? And that will be Thursday evening. And guess what? We're through with all the preliminary stuff. Hopefully I can get here right at 4 o'clock and we can get going on it, on the physics right at 4. All right, good deal. We did get a little ground to cover today, but not as much as I probably should have. Hopefully by Thursday, I will have you in a roll book as well.